So good evening, everyone. Thank you for being here this afternoon. And thank you to the chair for the kind introduction. Thank you to Stefan and the other organizers for inviting me here, giving me the opportunity to, first of all, attend this beautiful conference and present my work. And it has been really inspirational for me, I've learned a lot, but the thing that I really enjoyed, you know, the schedule is insane at this conference, a death march, but there are all these talks by young people, young investigators. It was amazing, and they are so beautiful. And I think this shows that this is a field that is interesting the next generation. So it's exciting. We have to see what will happen. So as you have heard, I'm a theorist, a modeler, and today I will talk about some of the work that my group is doing within metal organic frameworks. And I had the pleasure, the honor of being one of the theoretical collaborators of Omar Yaghi, and you have heard about his beautiful presentation on water harvesting using metal organic frameworks. And this is a picture of one of Omar's students a few years ago. You have seen this in the introductory lecture that Omar gave. And so the big question that we as modelers are trying to address is to understand the phenomena according to which these MOFs pluck out water from arid air on the molecular level. And I'm going to tell you a little bit of the story from a slightly different angle compared to what you have heard from Omar and Nikita yesterday. But I think I was thinking after Omar's talk, my greatest success, okay, sure, we did a very nice study, but my greatest success, I think, is that I have converted Omar to a computational and theoretical person. I mean, the first time, yeah, I need an applause. You know, a few years ago, I was at a conference with Omar, a Faraday discussion, and he was sleeping during all the theory and computational talks. And I gave him a hard time. And I thought he had no faith in what we're doing. Nowadays, he wants to become one of us. So I think we have been successful independently of how we have addressed this problem. But so the question here is, how can we complement the experiment to really try to gain a molecular understanding of these phenomena? And you have seen this slide before. This is the material with which our team, there are various teams funded by DARPA who are working on this project. Our starting material is this MOF2022, which is formed by this alumina oxide SBUs, and this is the linker, this H3PDC linker. And this is the adsorption, isotherm, and the desorption curve. And so the idea is, the challenge is that, okay, we have this material. Can we come up with a material that performs even better, especially in dry climate, but also can we really gain a molecular understanding? And so here is where the computer simulations and the role of computations come in. And so the point is that sometimes, from the experiment, you have a lot of information, but there are gaps. And so can the computation, so the simulations fill these gaps? Can they offer new interpretation? And as I told you, suggest new targets before their synthesis. And so what is the physics that we need to include in these simulations? So we're really studying phenomena where electron motions are included. So we need quantum mechanics, at least to understand phenomena at the molecular atomistic level. However, some of the phenomena that we have to study, especially when we want to compute adsorption isotherms and so on, are more ensemble properties. And in this case, we have to use classical simulations, Monte Carlo simulations. So I will tell you a little bit about how we have combined these approaches to understand the nature of these MOFs, which, by the way, is not this one. I will tell you about this MOF later, but I thought it was a cool video. And also how we have combined these calculations with machine learning. And from the computational theoretical point of view, this is a collaboration between my group and the group of Professor Joachim Sauer. So here you see, we see again the structure, and we as the theorists, electronic structure theorists, we are really interested in understanding the nature of all these possible binding sites. So you see here we have a OH group in the node, and here this could be as can act as a hydrogen bond donor or acceptor. And then we have this nitrogen on the linker, and this could be a hydrogen bond acceptor. And finally, here we have an NH group on the linker that can act as a bond donor. And so really try to understand the role as a donor, as an acceptor, is something in which you need this kind of calculations between the beautiful X-ray structure that Nikita produced cannot really explain these different roles. So how do we proceed here? So we start with some crystal structure that can be, I mean, as refined as possible. But then what we do, we perform DFT optimizations for the water-loaded MOF structures at different loadings. So we start putting in water molecules, and then we do ab initio molecular dynamics to identify the stable water-loader structures for about 20-30 picoseconds. And in such a way, we can identify the most stable water-loaded structures for different water loadings. So by following this protocol, my student, Soumil Chedda, he was really able to understand how each individual water molecule interacts. And as Omar has described and Nikita, basically these water molecules adsorb in unique sites through hydrogen bonds with either the node hydroxy or the linker pyrazole groups. And so here you see, I mean, we have seen this picture before, but what the theory can tell you. So first of all, we were able to really locate the position of the first water molecule. And these values that you see here, these bond distances, come from the computations. And we did, this was a sort of blind approach in the sense that we didn't know what Nikita would get out of his X-ray data. And these values are in quite good agreement with experiment. But also what we can say from these computations is that this first water molecule has these three contact points with the aluminum OH, so in this patch of the SPU, and with the NH and nitrogen, one acts as a donor and the other as an acceptor. And also we can estimate the binding energy of this first water molecule. And then the second water molecule comes in, and you see it's over there. We see the bond distances, and we see that again this water molecule has mainly 2 points of contacts, mainly with the linkers, and the average binding energy of the second one is comparable with the first. And then we have the second layer. So we start introducing the third water molecule. And so here things, again, this third water molecule is still mainly binding to the framework. So it's binding to the OH of the aluminum, and but also a little bit with the hydrogen of the first water molecule. And so you see also here the energy of this binding on average is slightly lower than the one of the previous two. So we are evolving to something slightly different. And then we see the fourth one, which instead has 2 points of contacts with the previously introduced water molecules. And the energy you see is also a little lower than the previous two. And so these four waters in a way create these sort of seeds to which all the subsequent water molecules will bind. And so it's I think it's important to see really have this this different angle that describes this problem. And of course, the point, as I told you, first of all, we want to have a sanity check and see that our results make sense. And so we compared them with the experiment of MOF303. And then the idea is, okay, can we envision modification of the linker, which plays this primary role in the way in which the water is adsorbed. And so the second MOF that was considered experimentally was this MOF303, sorry, 333, to be compared with 303 to see if one could avoid this shape of the isotherm here. And as Nikita said yesterday, yeah, the shape is smoother, but it's this increase is shifted to higher values of relative humidity, which probably is not one would like to achieve if one wants this material to work in a dry area. But so this is the isotherm experimentally measured. And so what we have done sequentially, so Somil has been also interacting with one of my colleagues at Minnesota, where I was before, Ilya Sipman, who is an expert in Monte Carlo simulation. And with Ilya, he has basically derived a force field for this system and performed some Gibbs ensemble Monte Carlo simulations. And this is a way to compute in a rather effective manner an isotherm. And here you can see we have the for MOF303 and MOF333, we have the experimental and simulated isotherms. And the agreement is satisfactory within what one expects between theory and experiment, also considering that there could be various arrangements of these waters in the pore, and we are making certain choices when we set up our simulation. But again, in such a way, we have developed a procedure that goes from first principle to these Monte Carlo simulations to identify the structure and compute isotherms. So what is the next step? So the idea is, again, we want to eventually engineer materials that are more effective. So we want to modulate the hydrophilicity of MOF303. And so we want to build hypothetical analogs of MOF303 by replacing the pyrazole linker with the other 5-member heterocycle linkers. It's already in principle what we have done going from MOF303 to MOF333. And so here what one does in a computer, okay, considers the building blocks. So we have the aluminum node, the linker, and then eventually consider this is a library of other linkers that we are considering also within this multivariate MOF philosophy. So we don't just consider one linker, but maybe a combination of different ones. And so we are working in this direction. We are utilizing theory and computation, but also machine learning. And so here, I want to show you a little bit about this overall procedure that we are using. So the idea is to collect a lot of data. Some of them come from this core MOF database. We heard a lot about it this morning in the theory sections, and variants of MOF303. And we generated about 10,000 MOFs, and then filter them, looking by making several considerations. Of course, the interaction with Nikita and Omar helps a lot, because sometimes we just come up with some structure and they say, oh, this makes no sense. But then we have this, we have some hypothesis generation engine that basically as an output gives some structures from the machine learning. And here you can see something that looks a little crazy, but this is a proposed structure with a mixture of long and short linkers. And then again, by talking to the experimentalists and by hypothesis testing guidance, what was suggested is to replace this biphenyl linker with shorter linkers to improve MOF hydrophilicity. And so this is the refined structure that one works with, and this loop continues. And again, I have to say, I mean, sometimes using loops like this, one comes up with structures that may look a little insane, but I think that even if they are unrealistic per se, they inspire all of us to think in a different way and maybe explore some chemical space that otherwise one would have not explored. And Omar told me that if I showed you the latest results that are not published, he would kill me, so I will not do that. But I can assure that now we have a very nice variant of this material, which has a very nice isotherm. So it's basically the saturation level is quite high, and stay tuned. Hopefully, we'll publish it soon. And again, it was something that, in a way, was inspired by these computations and this machine learning. Otherwise, probably we wouldn't have looked at that. Of course, the conversation with the experimentalist is always very important. So basically, this was an example of how this interaction between computational people, experimentalists, and also data scientists, computer scientists is very important. Of course, you know, we're given a big challenge. Basically, what I've told you is looking at these MOFs from the eye of the molecule inside here. But at the end of the day, the goal is to deliver a device to DARPA. And so one has to go from the molecular scale to the micropore scale, macro scale, and finally system scales. And here is where the other members on the team, so for example, Grant Glover is working more here between these two scales, and General Electric at the end of the day will try to develop this device. But I think that the understanding here can really make a difference, at least in coming up with the novel materials. So this was my first story. Now, in the second part, I want to tell you about something different, which is related to instead using metal organic frameworks for catalysis. So it's a slightly different topic. However, I think what I will do at the end is try to reconcile these two stories by showing you that when you have this self-sustained feedback between theory and experiment, one can draw conclusions that otherwise would have been difficult. And so what I'm going to talk now is a chemical reaction related to natural gas conversion. I mean, we have a center, it's a multi-university, multi-PI center funded by the Department of Energy in the United States, an Energy Frontier Research Center. And so far we have been focusing on looking at some natural resources and convert them in other chemicals that can be used as sources of energy. This is just an example. But the point is that for this kind of chemistry, MOFs seem to be good, ideal support for heterogeneous catalysis. And probably I don't have to convince this audience about the utility, the potential of MOFs. But the idea is that they can host well-isolated active species. And I was sharing before this session a catalysis section, and we heard a lot of beautiful talks about MOF being this support. And so the idea is that in principle, they are periodic, so one can achieve a uniform distribution of the catalytic sites. And also, because of the pore openings, there is an easy access of the reactant molecules to the active centers. Of course, we know that this is an idealized representation. We heard about defects in the previous session and other phenomena, but ideally this could be a nice platform with which we like to work. So now I'm talking about a different OMAR. It's OMAR Farah and a different MOF, not the Yagi MOF. This is a NU1000 made at Northwestern. I know that some of the OMAR's group members are here, so I'm sure they are familiar with this material. And so this is an NU1000 with a zirconium-based node. So there are these two different pores with different sizes. And then we have this node with 8 linkers. The node is this zirconia-based node. And in this particular case, the linker is this TBA PY linker. And within this context of carbon functionalization, one reactions that we have been looking at is propyne dimerization. And so a little motivation why we have been looking at these reactions. Alkynes act as catalyst poisons, and they should be removed from alkane polymerization feedstocks. And moreover, the dienes that one could form are important chemical intermediates for various applications, pharmaceuticals, insecticide production. So the goal here is to look at different MOF-supported catalysts for this conversion. And so in the initial study, our experimental colleagues, and so this is a Northwestern Argonne National Laboratory effort, they basically installed the metal at the node of the MOF using atomic layer deposition in MOF, which is a post-synthetic modification of the MOF. And then basically they studied this reaction, the propyne isomerization and hydrogenation. And so looked at these two different branches and considered different transition metals deposited on the node. And so here we see these are some initial experimental observation. So here you see different colors correspond. I apologize for those of you who are colorblind, but all these curves correspond to different transition metals deposited on the node. And we have the yield on the left, and here we have the selectivity. And so basically, even if you cannot read all the symbols, here we have some curves at the top that correspond to cadmium and zinc, and they are very highly selective towards isomerization. On the other hand, at the bottom, there is copper, which is not very selective towards isomerization. On the other hand, the favored product is hydrogen, so the hydrogenated product, so high selectivity towards hydrogenation. So the question is why, and that's where eventually they ask us theorists to try to rationalize these different behaviors. And so here there are some calculations performed by my student Ridish Pandahar. Now he's graduated. He works for OpenEye, and actually this is also a collaboration with Joachim. We have enjoyed. He's our advisor of the FRC, but sometimes he also gets so excited about our projects that he comes up with beautiful suggestions, and he is part of the project himself. And so here Ridish said, okay, we have a model. This is the zirconium oxide node, and then we have our metal installed on top of the node. And let's look at the two extreme cases. We have copper versus zinc. And so basically, this process can can happen in two fashions, that there can be a heterolytic or homolytic reaction. And here we have the two energetics for the two reactions. And you see, what basically happens here is that if one follow the bottom reaction, the homolytic, you see the oxidation state of the metal can go from 2+ to 1+, while in this case it remains +2. And so zinc wants to be +2 because it corresponds to an electronic configuration of D10. On the other hand, copper prefers to be +1 because it also corresponds to D10. And so here you see the energetics. Copper prefers reaction 2, while zinc prefers reaction 1. So basically, if we look at the free energy of activation of hydrogenation versus isomerization, we can say that in the zinc case, this reaction is preferred, while in the copper case, so this is not the case, but you see the homolytic dissociation is preferred in the copper case. And so this is what gives hydrogenation versus isomerization. So in a way, what we've done, we had this set of experimental data. They asked us to explain them, and by consideration of that comes from the computation, from general chemistry knowledge or inorganic chemistry knowledge, we came up with a plausible story, and this was kind of nice. But so what I've told you about is what I like to call the usual approach in catalysis. And in a way, it's the usual approach also in the previous project. So the experimentalists characterize a MOF catalyst. The theorists come up with a model. We have this metal on the top of the node. We have some disagreement to begin with, and then insightful experiments, more calculations lead to a compelling story. And this is, I mean, what happens in most of these calculations. However, there are some problems with this approach. The first one is that it's not scalable because the characterization is expensive, often insufficient, and it requires, I mean, to come up with a story, creative work and storytelling are necessary. And also, if you learn a lesson about one system, it's difficult to transfer to a different system. And so it's often unclear how to motivate further design. So when we decided to revisit this approach, this problem with a more comprehensive approach, and basically we decided that we wanted to integrate the experiment and the calculations also with some data-driven approach. And so the idea here is to collect as many as possible catalyst synthesis variables, again, information about reaction conditions, theoretical results from or features from the calculations, that kind of calculations that I showed you before, and then use them to construct a machine learning model that eventually will tell us about the next experiment. And so let's start, first of all, the experiment. So at Argonne, our colleagues, they really set up this autonomous synthesis and high throughput reactor. And the idea here is that they can really run many experiments, about 16 at the same time, and collect the data. All these experiments correspond, for example, to different reaction conditions. And here, let's see the results from the experiments. This is the Katie McCulloch. She's a postdoc at Argonne. And so here we can look, what we see here is the maximum hexadiene yield for different transition metals. So she looked at various metals. And at these reaction conditions, basically this is the outcome. So copper seems to have a yield of 16%. All the other transition metals are quite silent. And so copper is extremely promising, but the question is, with this integrated approach of synthesis, characterization, data science, and computation, can we achieve reasonable activity also with other metals based on what we learn from copper? And also, how can we prioritize copper while screening other metals? So here is where the machine learning procedure was introduced, and this is a work of my student, Daniel King, who basically came up with a dual model machine learning scheme. The first is quite simple. It's only about copper, and so the goal here is to predict the optimal copper loading and the optimal experimental conditions. And these are the features that he used to develop his machine learning model. So the copper loading, the temperature, the space velocity, and the reaction concentration. And then once this information was collected and some predictions on copper were made, then the idea is to go to model 2, which is a little bit more complicated, because we are not looking just at copper, but at all the other metals, and predicting which metals are good and what are the optimal conditions. And so here, these are the features used to develop this machine learning model. Of course, what we learn here is used also there. And so let's look at the first part. So this is the machine learning optimization of for copper. I call it machine learning. Is PCA. I don't know, maybe machine learning is a fancy name for PCA, but the idea is to have this. There are these vectors of the informations, and here we see the predicted total hexadiene yield for copper, and we have this dark spot here. So basically, these were the experimental points, and this is the predicted point, which corresponds to these particular conditions. So there are some observation to be made on this, and I think the first, well, first let's go to the second model. Let's see now, once we have learned these things about copper, now we go to model 2 and look at the other transition metals. And so these are the features that are entered into the model for all the different transition metals. The first three are the experimental parameters that we have learned from copper, and then of course we have one type of metal. We have some metal atomic features. These are really information about the metals, and some DFT features that come from the calculations, the kind of calculations that I presented before. And here, Daniel uses XGBoost tree-based regression model, because it's a larger feature space. So this is a more powerful model. And ideally, I mean, he comes up with some predicted metal yields and some suggestions on how to make the next catalyst. And so here, let's see the data. Here I reported again the initial screening that Propyne did without any of these help from machine learning and calculations. And now these are the current best performances. So here you see we have about 1,000 experiments. A large majority is on our copper systems, but then there are also these other transition metals. And so between the initial screening and the current situation, we see that with this iterative procedure, we have increased the maximum hexadiene yield for copper from about 16 to 25%. And these other metals also seem to be more interesting than before, less silent than before. So the question is, what did we gain? What lesson have we learned? And here again, you know, Omar said, oh, now only computational scientists are needed. I want to show you actually what I think we have learned from this exercise, but where we still need the interaction with experimentalists and theorists, and it's not just about data and big data. So the first thing, if we look at copper, that we have learned, and perhaps again the catalyst people may, so I want to make sure, I want to keep track of time. The catalyst people may tell me, well, this is obvious, but you know, when you are a theorist and you say, okay, calculate this for me, I have no idea what the reaction and synthesis conditions are, but instead they are important. You see, we have this spike here. So the yield spikes in this means I mean, the Goldilocks means the best optimal situation. And the other thing that we have to see is the most common yields is 0. So most of these reaction and synthesis conditions give a yield of 0. So you have really to choose that exact spot. But also, and for example, we heard these talks this afternoon before this session, but also this morning, are we looking at yield or selectivity? So here you see this is the yield picture, but here we have the selectivity for copper. And you see the Goldilocks spots are in different positions. So when we do a calculation, an electronic structure calculation, are we looking for this spot or for this spot? Also, I think the most important lesson that we have learned is that, I mean, after this subsequent theory experiment, Katie performed more characterization, and basically these plots show that this is in the case of copper. Basically, copper appears in the form of nanoparticles. So there are these large clusters, and this is probably the reason why copper is so active as a catalyst compared to the other transition metals. So the question is, okay, we have learned these things which are important. So why won't regular computational modeling work? And I would say alone, why doesn't it work? And here you see, these are the calculations, subsequent calculations that Somil Chedda performed. And Somil basically looked at this catalyst in which the model that is set up as one copper atom on top of this node. And so he could not predict the future. He didn't know that the catalyst is in the form of a nanoparticle. And so all these calculations with state-of-the-art methodologies, and that shows what is the rate determining step and so on, are performed on a system that is not so related to the real system. So now we are going back to a larger particles, a sort of nanoparticle. So at this point, I mean, you know, Omar told you, okay, we want to do MOF chemistry, reticular chemistry in a computer science department. So I want to cite you the words of this. This is a famous chemist, Roald Hoffmann. I'm sure many of you know him. And so he gave a talk a few months ago at a theory conference, and it was a very provocative talk. And so I want to read you these words. In view of the progress of machine learning and neural networks, it is likely that these two tools will compete efficiently in quality, in cost, with the best quantum chemistry tools in the near future. Then the community of number-oriented quantum chemists, and we are number-oriented, I think we all are, not just the quantum chemists, but we certainly are, will face a dramatic problem. Will their function be relegated to providing reliable training data sets for the production of improved neural networks? Or will they follow the destiny of supermarket cashiers these days and that of taxi drivers tomorrows? In other words, is quantum chemistry dead? And you know, I think this is a very important question that we are facing as a community. And Roald here, he told me that in this picture, he was playing chess with his grandson, and he was miserably losing. So he has this cloth to dry his forehead and some candies so that he can cheer up himself. And so I don't know. I mean, this is a big question, and in a way, Omar's statement made me also think: does he mean the same thing as this? But so here I want to, and I'm close to conclusion. I mean, I told you, okay, we needed machine learning to reach this achievement. Same story also in the water harvesting, even if I couldn't show you the results. But what can't machine learning do? And so here I think we have to be critical from all points of view. So here, basically, I told you, okay, with the machine learning, Katie reached these great results. But actually, you see here we have the maximum hexadiene yield over time. So these experiments, they started in May, in May 21, and now here we have after a year. And in the same picture, we have again time, and we have the maximum hydrogen concentration. And so basically, the first 3 months of the experiment were totally unsuccessful, 3 or 4 months. And then after a while, I mean, we were using this experimental data to train the machine learning model. There was no success in coming up with a reasonable catalyst. And then after a few months, the human made an executive decision, and she decided to expand the hydrogen concentration search space. And of course, I mean, at the beginning, she made the decision to work here because it seemed the first thing to test. And so only when this decision was made, then finally we started having interesting results. So maybe this is a trivial statement, but machine learning can interpolate well within a space, but it can never tell you the space is wrong to begin with. So we had to know when to make an executive decision to change the chemical space that we are looking at. And so I think that even if we need to work with computer scientists, I think that the human, so for the next generation, don't worry, it's not that you will be replaced by computers, because you are needed here to use your brain. And so at the end of the day, what have we learned? That the reaction and synthesis parameters are critical. And this is, for theorists, I mean, of course, it's a blessing, but for us, it's also a curse, because it's very hard for us to model computationally these critical conditions. But at the same time, we can tell convincing stories with high throughput data collection assisted by machine learning and analysis. And finally, when we use this machine learning data, we have to be cautious and know when eventually we have to make a change in the space that we are exploring. So to conclude, I mean, here we are here together, and we are, I mean, I'm a theorist, a computational, but we are all working together. And I think experiment is what brings us together. But we, as theorists, we really have to calculate, and not just calculate to provide you with a number, so you check a box. We have to understand with theory and computation. And so I always tell to my students, when they come to me with a number, what have you learned from that number, and how can you use it to teach something to the others? And this is what distinguishes us from computers, and we should always ask why we get a certain result and what it means. More on the big scale, I mean, can we achieve a quantum leap, for example, in the water harvesting problem or in catalysis? So from a computational point of view, we certainly need, we are dealing with very complex problems, and so we need to establish consistency between different frameworks. We certainly need better methods for these complex systems, and so it's important that some of us work on method development. We also need better algorithms for these problems and for the computers of tomorrow, exascale computing, quantum computing. And finally, what I think is the most important part is really we have to develop this closed loop holistic architecture with high throughput experiment and high throughput computation. With that, I think I've been good with my time, and I want to just finish by acknowledging, first of all, the external collaborators. So the water harvesting project is a very challenging project. And so I want to acknowledge Omar, Joachim, Nikita, Grant, David, and Ilya. And for the Catalysis project, Omar, Farah this time, Max Del Ferro, and Katie McCullough. And finally, this is my group. Of course, I've just told you about the work of these excellent people. So Somil has been working mainly on the water harvesting project, and Paul Kallio and Gotham are also working on that project, but they are more looking at the COF and machine learning aspect. And Daniel King and Ridish Pandahar are working on the Catalysis project. And with that, I'd like to thank all of you for your attention. And if you have questions, I will be happy to take them.
Thank you very much for the exciting talk. So are there any questions? If so, please feel free to use the microphones in the middle.
Aram Bogaev, Southern Federal University. Many thanks for the talk. It's always great to see when machine learning suggests some result and this result works. But as you mentioned about understanding, I'm sure you have some example when machine learning helps to find some correlations which human was not able to, which was not so obvious to find by human mind. But if you analyze the those PCA components, if you try to find what is the physical meaning of this PCA component, so maybe it's combination of some 2 or 3 parameters. So do you have these examples when machine learning provides understanding and not just the result?
So I think maybe maybe machine learning provides a solution, a suggestion, and then you ask yourself, okay, what's the physical meaning of that suggestion? And yes, this can happen, and that's why maybe then one makes the next informed decision of for example, changing the hydrogen concentration. We have some examples in the MOF design for water harvesting, in which we, for example, we see that the pore volume matters. And so we try to design materials or frameworks with a given pore volume, for example, or hydrophilicity, hydrophobicity. So we try to include groups that are more electron withdrawing, electron donators. Yeah.
Thank you.
Okay, I would like also to acknowledge the viewers which are watching us online. There is also one question coming from this audience. It's Varsha from India asking, or at first saying, excellent talk, thank you. I just want to know, in the water adsorption, when the second and third water molecules adsorb and start to interact with the already adsorbed first molecule, does the interaction of the first water molecule with the framework weaken?
Yeah, there is there is every time you add a water molecule, the framework rearranges. So yes, there is a rearrangement of the whole structure. So yeah.